In the vast field of aerospace engineering and space sciences, the exploration of celestial phenomena remains a source of fascination and inquiry. Using the power of data science, this report delves into two datasets sourced from NASA's Open Data Portal titled Meteorite Landings and Fireball and Bolide Reports. As an enthusiast of aerospace engineering and space sciences, my aim is to unravel patterns, discover trends, and contribute to a deeper understanding of extraterrestrial events through a data-driven lens. Meteoroids are small, rocky, or metallic bodies in outer space, and when they enter the Earth's atmosphere, they are referred to as meteors or shooting stars. If a meteoroid survives its fiery passage through the atmosphere and lands on the Earth's surface, the remaining fragment is called a meteorite. A bolide, or fireball, is a bright, exceptionally large meteor that often explodes in the Earth's atmosphere. These events are caused by the entry of a meteoroid or asteroid into the Earth's atmosphere, where it rapidly heats up due to friction with the air. The intense heat causes the object to glow and become a visible streak of light in the sky. This is NASA's Open Data Portal, where I accessed both of the two datasets. This page is the one corresponding to the Meteorite Landing dataset. Last updated January 31st of 2023, this dataset contains 134,000 views, 263,000 downloads, and plenty of information. The dataset contains 45.7 thousand rows with 10 columns of information. The columns with the information contain the following values: name, ID, name type, class, mass, fall status, time and date, latitude, longitude, and geolocation of the meteorite. Here is the webpage for the Fireball and Bolides report dataset. Last updated January 31st of 2023. This dataset has 11.4 thousand views, 6,070 downloads, 92 rows, and 10 columns of information. The information in each column are as follows: date time with peak brightness, latitude and longitude, altitude, general velocity, velocity in the components of x, y, z, total radiated energy, and total calculated impact energy. From these NASA web pages, I downloaded the datasets as CSV or comma separated value files and will be using the Google Collab platform to perform my analysis using the Python programming language and Pandas library. After downloading the CSV files into my Google Drive, I connected them to my Google Collab document. Then, I imported the Pandas library and assigned a variable to reference each dataset. I assigned the name DF1 or DataFrame1 to the dataset containing Fireball and Bolides reports, and DF2 or DataFrame2 to the Meteorite Landings report dataset. After importing both datasets into a Google Collab document, data cleaning and preparation for analysis was necessary. The initial focus was on DF1. Having identified columns with missing values, I filled these gaps with NA. Next, I added a new column named type with all the values set as Fireball/Bolide. This classification aids in distinguishing between entries related to Bolides and meteorites once I combine both datasets. Additionally, a geolocation column was appended utilizing the latitude and longitude values to establish a commonality between the two datasets. To ensure accurate temporal analysis, the date-time peak brightness column was converted to a date-time format. In the case of DF1, cardinal directions present in the latitude and longitude columns were either converted or removed. Specifically, north and east were removed to signify positivity. At the same time, south and west were replaced with negatives and repositioned at the front to indicate negativity, thus facilitating the extraction of numerical values from these geographical coordinates. Next, I moved on to DF2. Like my process for DF1, I began with filling all missing values with NA. I then added a type column to show these rows corresponded to meteorites. Lastly, I converted all columns containing a numerical value into integers or floats, rather than their original object or string type. Finally, I got to the point of combining the two datasets into one. To merge two datasets into one under the variable of df, or data frame, I completed an outer merger. This outer merger used the columns geolocation, type, latitude, and longitude because they are present in both datasets. Now that all the datasets are cleaned and combined, I was able to begin my analysis process. First, I individually analyzed the Bolide, or DF1, a Meteorite, DF2 datasets. Then I went on to find trends and patterns between the two in the combined DF dataset. According to this bar graph depicting the frequency of bolide appearances over time, a noteworthy surge in bolide sightings occurred in 2012, with a peak observed in 2014. Further investigation may shed light on the factors contributing to this increase, potentially pointing to an external cosmic event. Analysis of the velocity component graphs reveal a low positive correlation among the different velocity axes being x, y, and z. It seems that if the velocity in a certain component is high, it is presumable that the others will have high velocities as well. This bar graph presents the frequency of velocities from bolides in the dataset. The majority of velocities in the x component range between -20 to 20 kilometers a second, in the y component from -20 to 15 kilometers a second, and in the z component -17 to 17 kilometers a second. The most common overall velocity hovers around 18.5 kilometers a second. From this visualization of bolide peak brightness frequencies at each altitude, I noticed bolides tend to shine brightest at an altitude of approximately 28 kilometers, as demonstrated by the tallest bar. Contrary to my expectations, the total radiated energy versus velocity graph suggests a minimal correlation between component velocities and total radiated energy. This absence of correlation is echoed when calculated total impact energy is put in relationship to velocity. Nevertheless, a comparison of calculated total impact energy versus total radiated energy indicates a clear and direct linear relationship between the two values. Now, let's move on to analyzing DF2, or the Meteorite dataset. Several insightful revelations emerge from this dataset. Firstly, the fall data highlights that the majority of meteorites are found rather than actually witnessed during their descent. This observation aligns logically with the fact that numerous meteorites dating back millions of years have landed on Earth and persistently await discovery. Notably, an intriguing pattern surfaces in the meteorite landings over the years, revealing a substantial increase in meteorite discoveries post-1975. I infer that this surge may be attributed to heightened NASA funding following the space race, enabling the agency to undertake extensive exploration and research endeavors. Examining the class distribution pie chart, it becomes apparent that a significant portion of discovered meteorites belong to the L6 class. The L6 classification signifies an ordinary chondrite characterized by a moderate degree of alteration in a specific composition featuring a lower quantity of metal. Turning attention to the scatter plot depicting calculated total impact energy versus altitude, a perceivable but low correlation between altitude and impact energy is evident, with a few outliers challenging the trend. Finally, let's move on to the combined DF dataset. From these geolocation maps, meteorites exhibit high concentrations in several regions across the globe, including the United States, southeastern parts of South America, Europe, Asia, Australia, Northwest Africa, and Southeastern Africa. Conversely, areas such as Canada, Greenland, and northern regions of South America have few recorded meteorites. Notably, meteorites have also been discovered in oceanic regions, hinting at the likelihood of numerous unobserved instances. It's conceivable that many meteorites may have landed in remote oceanic areas, icy regions displaced due to climate change, or have become obscured by land over time. Additionally, we can see that meteorites are far more common than bright and noticeable bolides. This supports outside research I found, which explains that bolides typically involve larger celestial objects entering Earth's atmosphere. Half are invisible in sunny skies, and many occur over uninhabited oceans. It was incredibly enlightening to complete an entire data science report that involved analyzing 2 of NASA's datasets that I was truly interested in. This project improved my knowledge of cosmic events and sharpened my data science abilities. The Fireball and Bolide reports, along with meteorite landing datasets, served as a window into the fascinating realm of celestial bodies, offering insights into their frequencies, velocities, and energetic characteristics. Throughout this project, I not only acquired valuable data science skills, but also developed a profound appreciation for the intricate dance of cosmic entities, underscoring the interdisciplinary nature of data science and unraveling the mysteries of the universe. If you enjoyed watching this video, please make sure to like and subscribe.